I'm Gene Chen, Yokogawa Stardom Product Manager. Today I'm going to cover Stardom's liquid library that's based on the API MPM liquid oil correction factor standard. Specifically, that's the API MPM Chapter 11.1 standard that covers temperature and pressure volume correction factors for generalized crude oils, refined products, and lubricating oils. So I'm going to start off with the API MPM 11.1.6.1 algorithm, which is the method to correct a measured volume to customary base conditions and density from customary base conditions to an alternate temperature and pressure. So what I've done is I've gone ahead and set up an Excel spreadsheet that acts as an OPC client, or it is an OPC client to an actual controller. So I can make entries in this area of the spreadsheet where it says custom entry here. And as I make entries into the spreadsheet and I click on the button, clicking this button will then send that data to the controller, and it will be read back here. As it's read back, this will then match these entry data that's listed on the right hand side, and then also the output we put into this lower part where it says outputs. These outputs will actually be read back from the controller. So I can show you that in the engineering environment, so you see what that looks like. Here is an example of some of the function blocks. This is the Chapter 11, Part 1, Subsection 6, Subsection 1, and that is the one we're going to be interested in going over first. Outputs come from here, this right-hand side of the function block, and they're written back to the Excel spreadsheet, and the configuration inputs are on the left-hand side, and so it reads it from the Excel spreadsheet, places them into these inputs, and then the right-hand side here is the outcome of the calculation. So again, the left-hand side of this function block, that's populated by whatever I enter here. We do a read back from the controller to make sure that what was the controller accepted was what we actually input, and then we can see the results on the bottom, and this matches with the right-hand side of the function block. So I can do a free entry here. I can say pick out a commodity group. You can see I put some little help bubbles here. So your choices are 1, 2, 3, or 0. 1 is a general crude oil. 2 means a refined product like fuel oils, jet fuels, transition zone, or gasolines. And a 3 indicates a lubricating oil, and 0 would be some specialized liquid. And if you use a 0, then you'd have to supply an alpha 60 number that you've already calculated from the field. The other little help bubbles here, you need to indicate at times what pressure units you've used, if it's PSI, kilopascals, or bars. And then also we have density units. We need to know if the density measurement was in kilograms per cubic meter, or if it was API gravity, also known as degrees API, or if it was relative density. And then also at the bottom, if there was an error, there's an error indicator. If there's an error on the block for whatever reason, this error would become true, and then it would throw a status code, and the status code little helper here tells you if it was due to temperature not being within range. So these calculations are only good within a certain temperature range, pressure range, and density, and so that will be displayed here under the status bar. And these statuses, I'll go back to the engineering environment. You can see that there's the error and the status codes on these function blocks. So they are there, and it's documented. If you right-click on the function block itself and click on Help, there's a description of the function block itself. As you scroll down through it, you can see that, it talks about the commodity groups, what they mean, which commodity group to use depending on what type of oil or that you have, or petroleum that you have. And then it talks about, here's the alpha 60 inputs. These are the different inputs and outputs to the block. To give a little help, it has a little table showing you the error and status codes, what they mean. And so all this is contained within our new library. All this help and information comes as part of the library. So go ahead and close that. Another thing I wanted to point out is just kind of the conventions. As I said, the CG is commodity group. A60 stands for alpha 60. Any capital T stands for temperature, and then the small letter after it will designate what's the temperature condition at. So O is observed conditions, B stands for base conditions, and a little a would stand for alternate conditions. Another convention, a 3-letter code convention, so use underscore And then BGO here, shown here, means base given observed. So what I've highlighted here is CTL. The CTL, of course, is the correction factor due to temperature. And the underscore BGO means it corrects from the observed conditions to base conditions. So in other words, it gives you the base given the observed. So you measure the observed, and then you want to correct and calculate what the base condition is. That's what BGO means. F sub P is the compressibility factor, and that's for pressure. So that's used to generate or calculate the CPL, which is correction factor, the volume correction factor due to pressure. And then something new in the API MPM standard, this latest one, is something called CTPL, and it's the combined temperature and pressure correction. So that's what CTPL stands for. It's the correction factor due to temperature and pressure for the liquid, and raw is the unrounded value. And so you use CTPL raw to correct density, and then you use the rounded CTPL to correct volume. So that's the difference between these two. CTPL raw is just, that's the raw value. CTPL is the rounded value. And that's why if you look over in the results, you can see that this is the full unrounded value using long reals, and then this is the rounded value, rounded to 5 decimal places per the API MPM standard. Right here you'll see a V60. So the 60 stands for customary base 60 degrees Fahrenheit condition. And if it's a metric or any alternate conditions, then I just go with it would be like a VO for observed, volume at observed, or V sub A, which would be alternate conditions. So if you see a number there, the number like 60 means customary base 60 degrees Fahrenheit. If it's a letter that's used, then that is the letter designates what the condition is. O being observed conditions, B being base conditions, B generally being metric base conditions versus customary base, which is 60, and then A is alternate conditions. So those are the naming conventions I've used. And this holds true throughout all the calculations and examples. I've actually pre-programmed or pre-entered all the test cases that are published in the API MPM standard. So this is for 11.1.6.1. Example 1 here corresponds with the API standard, example 1. So as you can see, this is the API standard, the PDF format of it. This is the first test case scenario called example 1 under the same algorithm code here, 11.1.6.1. And let me go ahead and shrink this a little bit, and you can see where they match. So first it says this is for generalized crude oil, so that's a code of 1 here. You may recall that I said a 1 corresponds with general crude oil, so that's how we got the 1 there. And then it wants to have an input of minus 27.7 as the alternate temperature. And so we can see here where the T sub O stands for observed temperature, or in this case it's alternate temperature. That's minus 27.7 degrees Fahrenheit. And then we are asked for 0 degrees PSI. So you can see P sub O is the 0. Then it's asking for us to input a base, a density in degrees API 7.785. You can see that 7.785 is here. And then we're to input a volume of 987.99, and you can see that corresponds with that here. So I'll go ahead and shrink this. If I click on this example button, what this example button does, it takes the information from the example, inputs it to the controller, so it gets written to the controller, it reads it back here, places it here, and then the results are shown here in this brown or shaded area for easy comparison. What I've done is I went ahead and put in a lock on or freeze pane on the table here, so as I scroll through the different examples, because there's multiple examples per algorithm, you can see that it shifts, so you can see that this allows you to have your example right next to the results, so that you can have easy comparison. So if I do, for another example 6, you can see that the inputs here read back from the controller from example 1. If I push the 6, you can see that example 1 changed to example 6, and then these values and the inputs changed, and also the results output also changed. And you can see that they very closely match with the expected output. You can see right here, in fact they all match perfectly except for the observed density. So the density corrected to observed conditions. If we go all the way out to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places, you can see we have ends in 5958, where here in the API standard it ends in 596. So you can see that they rounded from, I have the 5958 here. That, if you count the decimal places over, you'll see that they really ended right there on the 5, and they rounded this 58 to 6. So you're there, see here, they don't have 958, they just used 96. So that was just, that difference is just in the rounding. If I rounded this to the same number of decimal places, that 958 would just become 96. So it's a perfect match. Okay, so I can kind of go through this and kind of show you how the table works. If you were able to have a representative there with you, our Yokogawa rep could sit down with you and go through the samples, and if you had your own data you wanted to enter, then you could do that at the end. I have this custom entry box here, so you could enter in your own data here, and then you could compare these results against something you've already computed yourself. So that's the test cases for 11.1.6.1. If I go back here to show you in the controller, I think we just did example 6. So if you look in the controller, you can see that, I'll just pick out some key areas to look. It was commodity group 2, density was 657.3, and the volume input was 14.72. So if I go back and look at the Excel spreadsheet for, let me go here to example 6, it's commodity group 2, and the density was 657.3, and then the volume was 14.72. So you can see that those were indeed what was sent to the controller. You can see that it was reflected in the controller itself, and you can see these results, 15.2973184 right here. We go to the controller, we can see that 15.29783.184 is indeed the output of that function block. And then if I go back to the Excel table and I go look at example 1, I'm just jumping around a little bit so you can see a big change. I can push this button. Now this new data is sent out to the OPC, via OPC to the controller, and then read back. You can already see that the temperature changed, the density also changed, so, and the volume changed. So the new volume input is 987.99, and then the new volume output should be 1020.6035499. I point that out because that's what's being corrected, right? The volume and also this density are what's being corrected. And if I then go out to the engineering environment, I can look at this. You can see indeed the volume inputs changed to 97.99, and that density at observed conditions corrected to customary base conditions, which is 60 degrees Fahrenheit in this in the United States, is 1020.6035499. So it's a perfect match. So we can go ahead and go through these individually at your leisure. I guess I can do that for you. So I'll push this, and you can see that the example 1 perfectly matches. Right? If I go down to the next one, say example 2, you can see that that now also perfectly matches out to 8 or more decimal places. And remember, only 8 decimal places is required for compliance with the standard. And in this case, we show greater than 8 decimal place matches. And then we can go to example 3, do the same thing. Okay, so I'll go ahead and go to the next one. I have several of these to do, and I'll just go ahead and do all these one at a time, so you can be comfortable that all our algorithms match for all the test cases that are in the API standard. So test 5, you can see if that matches. Then we'll go to test 6. And you can see that these also match. And you can 7. You can see again, once again, they match perfectly again with the results we listed. So next we go to 8. And then after the 8th example, the other ones are checking to see if we range checked some of the values properly. So they're not actually calculating all the way out all the output values because there's a problem. And according to the API MPM standard example, there's supposed to be a problem and we're supposed to catch that in the algorithm. So if I do example 9, push that button, you say, boop, there it is. There's an error. It went true. And it throws a status code of 1. Status code of 1 says temperature, says temperature input is out of range. And if I look in the standard, it says just that error in the TO, which is the input temperature, observed temperature is less than minus 58 degrees Fahrenheit, which is true in this case. Okay, that was probably a little long explanation going through each and every calculation point, but it gives you an idea that how well we match with API standards. And I'll generate another video for the other 5 liquid calculations, 11.1.6.2, 6.3, 7.1, 7.2, and 7.3. Thanks for spending the time with me, and I'll look for the next videos if you're interested in seeing those calculations as well.